We are doing chapter electrochemistry, and we have done in the last video some questions based on the standard electrode potential and Nernst equation. So today let us apply some more important concepts like standard Gibbs energy of reaction, conductivity, molar conductivity and self constant to solve some more questions. We will be doing NCERT exercise question 3.6 to 3.10. So the very first question, in the button cells widely used in watches and other devices, the following reaction take place. They have given you the chemical reaction and we have to find out the value of standard Gibbs energy and the cell potential. They have given you the value of standard electrode potential for the two half cells or two half reaction. So first let us write down the reactions taking place on anode and cathode. So at anode, that is negative electrode, we know that oxidation will take place, and here in our case your zinc metal is undergoing oxidation to produce zinc ion, which are going into the solution by the loss of 2 electrons. And at cathode, which is the positive electrode reduction process is taking place, and here your silver oxide in the presence of water is undergoing reduction to silver metal, and we are having the production of hydroxide ion which are produced in the solution. So in the second process, 2 electrons are being added which are being lost from the first half reactions. So therefore number of electron lost is always equal to the number of electron gain, that is loss and gain is always equal, and it is of 2 electron in this balanced equation. Now we will find out the net equation by adding these two. So zinc solid plus silver oxide Ag2O plus water is giving you Zn2 plus aqueous plus 2Ag plus 2OH minus ion, which are going into the solution. Okay, so this is our net reaction. Now we have to find out the E naught cell. So E naught cell is equal to standard electrode potential in case of cathode minus standard electrode potential in case of anode. In our case, cathode is the silver one, so we will write down E naught Ag plus over Ag minus E naught Zn2 plus over Zn. Always remember, standard electrode potential is the reduction potential. So we will put down the values. It is 0.8 volt minus 0.76 volt. So we are getting value as 1.56 volt. So your E naught cell is equal to 1.56 volt. This is our first answer, but we have to calculate the standard Gibbs energy also. So that is your delta G naught. This is equal to minus NF E naught cell, where your E naught cell we have calculated, and F is the Faraday's constant, and number of electrons involved in this case is 2. So it will be minus 2 multiplied by 96500 your coulombs per mole multiplied by 1.56 volt. So you will be getting here value as 3.010 into 10 raised to the power 5 joules per mole. This is our second answer. I hope it is clear. Come to the next question. Here it is given, define conductivity and molar conductivity for solution of an electrolyte and discuss their variation with concentration. Okay, so first one is we have to define conductivity. Now before defining the two terms, I'll have a look here on this apparatus. Here we have given you arrangement, how to find out the conductivity or molar conductivity or the resistance and resistivity for any electrolyte solution. This is called as conductivity cell. Here we are having two inert electrode and which are connected to each other via external circuit, and these are basically platinum electrode, and these electrodes are coated with finely divided platinum, and they are having a cross-sectional area or A, and the distance between the two electrode is L. Okay, so this A and L we will be using in our definition, so that you are not having any confusion from where we are getting A and L. Now, conductivity, the first one. Conductivity is represented by symbol kappa, and it is the reciprocal of resistivity. Okay, so we have given, according to this, it is reciprocal of resistivity, and therefore your kappa is inverse of the resistivity. And you know what is resistivity? Resistivity can be related to the resistance and the dimensions of the cell, as we have mentioned here in this case by this formula. Therefore your conductivity is equal to G into L over A, where L and A we have already defined, and G is nothing but inverse of resistance, that we call as conductance. Okay, so this is the conductance. Now if length is 1 centimeter, that is this gap is 1 centimeter and cross-sectional area is also 1 centimeter, then in that case your conductivity is equal to conductance, and therefore we can define in the same manner that conductivity of an electrolytic solution may be defined as the conductance of 1 unit volume of solution kept between two platinum electrode with unit area of cross section and at a distance of a unit length. Okay, so here L is 1 centimeter and A is also 1 centimeter square. In this case your conductivity is nothing but the conductance. Okay, or in other way we can define as conductivity is the conductance of 1 centimeter cube of solution of an electrolyte. Okay, so if we take 1 centimeter cube solution of any electrolyte and we find out the conductance of this with the any instrument, then in that case this conductance is nothing but conductivity. Now SI unit of conductivity is Siemens per meter, and but the more usable form that we use in lab is your Siemens per SI unit is Siemens per meter, but more usable form is the Siemens per centimeter, which we write as Siemens is nothing but your S is nothing but it is inverse of ohm. Okay, so therefore we have written here as per ohm per centimeter. Okay, this is more usable form, but SI unit is Siemens per meter. Molar conductivity. Molar conductivity is of a solution is the conductance of volume V of solution containing 1 mole of electrolyte kept between two electrode with area of cross section A and a distance of unit length. Okay, so when we apply this idea, then in that case your molar conductivity is nothing but the conductivity of a given volume V, where when the distance between the electrode is taken as unity. Okay, so if L is 1, in that case molar conductivity is equal to conductivity multiplied by the volume of the solution. But the actual formula that you are going to use for the calculation of molar conductivity is this one, your conductivity multiplied by 1000 and divided by the concentration term. This concentration term is any concentration term that you use in lab, and most of the time this concentration term is the molarity. Okay, that is concentration in moles per liter. Now SI unit. Your SI unit for this is Siemens centimeter square per mole. Why? Because it is for 1 mole of the solution, or we can write it as per ohm centimeter square per mole. Now, second part of this question, variation of conductivity and molar conductivity with concentration. How we have variation? So we will do one by one. The first one, the conductivity. Conductivity always decreases with increase in concentration. Okay, and this is applicable in both the cases, in the case of your strong electrolyte as well as weak electrolyte. Okay, why it is happening? Conductivity, why conductivity increases always decreases with decrease in concentration. Why? Because when we decrease concentration, then number of ions of a specific type will also decrease, and current is carried by your conductivity is basically because of the charged particle which are ion. So if we are decreasing the concentration, we are also reducing the number of ion produced in the solution, therefore conductivity will decrease. So this is because number of ions per unit volume that carry current in a solution decreases on dilution. Okay, now second part, molar conductivity. Your molar conductivity increases with the decrease in concentration. Okay, it is just reverse. Molar conductivity will decrease if we increase concentration, or it will increase with decrease in concentration. Why? When we are decreasing the concentration, your molar conductivity is increasing, just reverse of the conductivity. Why? Because when we increase the when we decrease the concentration, we add more amount of solvent, therefore we increase the volume. Okay, so what is the reason for this? This is because the total volume of the solution containing 1 mole of electrolyte also increases. So we have written previously, we have given this formula, that is molar conductivity is equal to conductivity into volume. Okay, so just a moment. Your molar conductivity is equal to conductivity into volume when L is equal to 1. Okay, so what we are having here, if we are decreasing concentration, we have given that if we decrease concentration, conductivity will also decrease. So when we decrease the concentration, value of K will decrease. Okay, but when we are decreasing the concentration, side by side we are increasing the volume, because concentration we decrease by adding more of the solvent. Okay, so therefore decrease in the value of K is very less than the total increase in volume, therefore overall value, that is molar conductivity, will increase. Okay, so therefore it has been found that decrease in your conductivity of a solution is more than compensated by increase in the volume, because we have given this with this formula. So you have to remember this idea always, that conductivity always decreases with decrease in concentration, and molar conductivity will increase with decrease in concentration. Next question, 3.8. It is given the conductivity of 0.20 molar solution of potassium chloride at 298 Kelvin is this. Calculates its molar conductivity. So we will put down the value simply in the formula of the molar conductivity. What information we already have? We know the conductivity. Conductivity value is given as 0.20 mole, and the second value which is given to us is as this is the concentration. So a molar conductivity value is this one. And they have given a solution. We have to find out the molar conductivity. We have written the formula that the molar conductivity is equal to conductivity multiplied by 1000 and divided by concentration in terms of molarity. We have written C here. C means in our case it is molarity. So we will simply put down the values. So values, the first value which is given to us is 0.0248 Siemens per centimeter multiplied by 1000 divided by the value of molarity is given to us. It is 0.20 m. So after calculation and simplification, when we simplify the units also, we will be getting the value as 124 Siemens centimeter square per mole. Okay, this is the molar conductivity. So this is our answer. Simply we have to put down the value and we have to calculate. 3.9 the resistance of a conductivity cell containing 0.001 mole KCl solution at 298 Kelvin is this one. What is the cell constant if the conductivity of this solution is this value? So they have given here in this question two values. They have given first the resistance value. Resistance is given as 1500 ohm, and the second value they have given is conductivity, and conductivity value is this one. Okay, and what we have to calculate, the cell constant. Okay, so cell constant, which depend upon the dimensions of the cell, is basically given by the distance between the two electrode, which is L, divided by the cross sectional area of each electrode. Okay, and this is equal to your conductivity divided by the conductance. Okay, from where we have got, we know that conductivity is equal to the conductance into L over A. Okay, so here G is the conductance. Now we can write we can rearrange this equation. So this is equal to what we have, your in place of K, in place of G, what we can write, it is 1 by G. 1 by G is nothing but the resistance, so multiplied by R. How we are doing this? We are placing in place of 1 by G. As we know that 1 by G, that is inverse of conductance, is nothing but resistance, R. So it will be this value. Now we will put down the values and we will calculate the cell constant. So cell constant in our case is equal to the first value which is given to us, that is your conductivity value, that is 0.146 into 10 raised to the power minus 3 Siemens per centimeter, multiplied by the second value, that is 1500 ohm. Okay, we will multiply this and we will be getting the value of cell constant as 0.219 per centimeter. Okay, always remember that your Siemens is nothing but per ohm. So accordingly you will be finding out the final units for the answer. So cell constant is basically this value. Now come to the next question. The conductivity of sodium chloride at 298 Kelvin has been determined at different concentration, and the results are given below. They have given you in the two columns. In the first column, they have given you the concentration, and concentrations are given in terms of molarity. And in the second one, they have given you conductivity multiplied by 10 raised to the power 2, and it is given in the unit Siemens per meter. What we have to calculate? We have to calculate molar conductivity for all concentrations, and we have to draw a plot between molar conductivity and square root of concentration. Okay, and from that we have to find out the value of the limiting value of molar conductivity, that is molar conductivity when concentration is 0 or tending to 0. So with this your table which they have given you, we will use this table or this data to find out the values, and then we will prepare a new table. Okay, so we will see how we will prepare a new table. first one. First is that we will, your value of conductance is given as Siemens per meter. This one, Siemens per meter. This is the SI unit, but we will be using in lab unit as Siemens per centimeter, because the cell constant is also in terms of the unit centimeter. Therefore, we will convert this Siemens per centimeter per meter into Siemens per centimeter. And what is the idea? That 1 Siemens per centimeter is equal to 100 Siemens per meter. Okay, and therefore we can write it as 1 Siemens per centimeter divided by 100 Siemens per meter is equal to 1. This is your unit correct conversion. This is you needed for the unit conversion. Okay, so we'll do this unit conversion for the value of your conductivity. Okay, now in your table, it is the value of conductivity is being multiplied by 10 raised to the power 2. Okay, so we will find out how we will find out the value of conductivity from this. Your 10, for example, we will take the first observation. Okay, what is first observation? First observation is this one. Sorry, first observation is this one. This is your conductivity value. Okay, so what we will do, we will write down the value as such as given to us. So it is 10 raised to the power 2 multiplied by your conductivity is having value 1.237 Siemens per meter. Okay, so therefore conductivity is having value 1.237 into 10 raised to the power minus 2 Siemens per meter. And when we convert it into centimeter, what we will be doing, this is equal to 1.237 into 10 raised to the power minus 2 multiplied by 1 Siemens per centimeter divided by 100 Siemens per meter. So we will be getting here value as 1.237 into 10 raised to the power minus 4 Siemens per centimeter. Okay, and this is the value that we are putting it here. Okay, the first value was this, and the value in terms of Siemens per centimeter is this one. I hope it is clear. So in the same manner, we will convert all the values and we will find out the values in the form we require. One example of first value I have shown to you. Okay, now for calculating the molar conductivity, how we can calculate, because we have next column of molar conductivity. So the molar conductivity is calculated by the formula 1000 into conductivity divided by the molarity. So for the first value it is 1000 multiplied by 1.237, the value we calculated, into 10 raised to the power minus 4 divided by concentration in this case is this value. So concentration is what? 10 raised to the power minus 3. So we are getting this value as 123.7. Fine. So this is our second calculation here. This one we have discussed already. Now the last part of this, that is C raised to the power 1 by 2. How to get that value? So concentration is given to us. The very first column is of concentration. So we will take square root of that. Square root of 10 raised to the power minus 3 will give you the value 0.0316. This is nothing but what? This is C raised to the power 1 by 2, or molarity raised to the power 1 by 2. This is our last value in the first column. So in the same manner, the way we calculated all values for the first one in this table, we will calculate the value for second, third, fourth and fifth observations, and these 1, 2, 3, 4 observations are already given. To avoid confusion, I am numbering them so that it is not creating any confusion. This is first observation, this is second observation, this is third observation, this is fourth observation, and this is fifth observation given in your question. And here the same observation we have written in a better form. This is your first observation, and this is second one, this is your third one, this is your fourth one, and this is your fifth your value or the data which is given to you. From these values which we have written here, next we will plot molar conductivity, which is here we have calculated already, and with your concentration raised to the power 1 by 2, which is our last column. Okay, so this value and this value we will plot. That is, we will plot this on your y-axis, and this one we will plot on x-axis. And after plotting and putting down these 5 points, okay, what are these points? Basically, this is our first observation, this is second one, this is third one, this is fourth, and this is fifth one. We will getting 5 points and we will get a straight line. Okay, and this straight line is showing that molar conductivity is what? Molar conductivity is increasing with dilution. Okay, now we have to find out the value of your molar conductivity when concentration is tending to 0, when C by here, when C raised to the power 1 by 2 is what is, it is equal to 0. We have to find out the value of molar conductivity in that case, and this value is nothing but this intercept. Okay, so the value here, it is this one. This is 124. So what we will write here, we will write down the value. Your molar conductivity, which is basically the intercept on y-axis. So this value is limiting value of molar conductivity. This value is 124. We will put down the scale which we have written here. So it is Siemens centimeter square per mole. This is our answer. Okay, and how we are writing down this value directly? Y-intercept is equal to the molar conductivity, which is having the limiting value. Limiting value of molar conductivity is given as intercept. Why? Because you have to remember that for strong electrolyte, we will get a straight line, and the equation of the straight line that we get after plotting these two will be this one, minus AC 1 by 2. So when we plot here, have a look here on your x-axis, we are plotting your 1 by 2, concentration raised to the power 1 by 2. This is on your x-axis, and on the y-axis we are plotting here the molar conductivity. So this is your molar conductivity. So in this case, what is intercept? In our intercept is nothing but what? Intercept is molar conductivity, which is having the limiting value, or the limiting value of the molar conductivity. Okay, so this is all for today. We will continue this chapter in the next video. I hope all solutions